Are you worried about lunar regolith yet? I mean, I feel like I've talked about it quite a bit, and just how the stuff on the moon is quite dangerous. It's small, jagged particles that gets into everything, wears down, seals like on your gloves, into all of the bearings in your spacecraft, even gave the astronauts stuffy noses and coughing when they breathed it in. And so mitigating the lunar dust is going to be a big problem. What can we do about it? I had a chance to ask all these questions to Dr. Christine Hartzell. She is a researcher at the University of Maryland and recently published a paper looking at the different strategies for mitigating lunar regolith. And the range of solutions are pretty cool. Like you can imagine trying to control it with electrostatic charges. They even have designed a lint roller that is based on gecko pads to be able to remove this dust. So it's a big problem. There are a lot of solutions, but it's probably going to be more complicated than anybody expect. I also talk about the versions of this with the Martian regolith and how it's been so tricky to remove the dust from the various Mars spacecraft. And it has actually taken many of them offline. And we cover all of the why don't they just ideas that people have proposed to me. So it's an interesting conversation. If you aren't troubled by lunar regolith yet, after this interview, I think you will be. All right, here's the interview. When you look at lunar regolith under the microscope, what does it look like?
So it's very angular. It's kind of sharp, jagged, small little pieces of rock. There's a pretty wide size distribution. But since the moon doesn't have water, doesn't have wind, there aren't these forces that cause grains to collide and roll over one another. And that's what would break the sharp points that we see. So that's why we don't see a lot of rounded grains like you do in sand on Earth. So the regolith is very angular.
And for people wondering, that's Christine's cat in the background, hoping for some kind of attention. So we will just wait a second, Katie. 30 minutes. That's all we ask. So is there like an analogy on Earth? Like, do we have a kind of material that looks similar to lunar regolith?
Yeah, so a lot of times when we're looking for like a natural simulant on Earth, we'll use like volcanic ash or like small pieces of rocks that are from volcanic flows, because sometimes those are very angular as well.
And then over time, as the forces of wind and water work on the regolith, or sorry, on the volcanic ash, yes. yeah, the simulant, then it wears it down and makes it a lot smoother.
Yeah.
And how long does that process take on Earth? Like if you have a fresh ash flow, I'll give you an example. When I was a kid, we had Mount St. Helens go off near where I live, and we were covered in ash. We had this, and I was far, I'm several hundred kilometers away from when the explosion went off, but it rained ash for a couple of weeks and we had a coating on it. And I've got a bottle of the stuff. Yeah. And it's very strange and gritty and kind of squeaky.
Yeah, I also have like a little Mount St. Helens sieved into different size categories thing. And I'm from Washington State originally, so I think that dust has kind of been in my background. But I don't actually know the exact time scale. I mean, I think that pretty much like very quickly once those small particles hit the ground, right, they're exposed to water, they're exposed to all these different contaminants like, regular dirt, the sort of humusy stuff in your soil, right? Like all the things that we have on Earth that give us life on Earth that you wouldn't have on the moon. So I think you would have to, if you could collect this volcanic ash very quickly, like that would probably be a pretty decent simulant to use. But as soon as it hits the ground and starts interacting with other stuff, then it gets kind of contaminated. That's why if we do talk about using a simulant from a volcanic area, it's usually in some place that's very dry, very kind of a deserty environment. So we don't have a lot of these like organic contaminants.
And chemistry-wise, Are they similar as well? Like if you find this volcanic flow that is in a dry region and you're able to collect the ash quickly, is it chemically very similar to what you see on the moon?
So some of the regolith on the moon is volcanic, so some of that is, somewhat chemically similar. But the moon also has regolith that's produced due to impacts. So you have like a big meteor, it comes in, it hits the surface, and when that happens, you can get melting. So this melting of regolith can also make these kind of small like glass beads in the regolith, and that's not something that you would see on Earth. So there's definitely some chemical similarities and some differences as well.
So the simulated regolith only takes you so far.
Right. Yeah. So like the stuff that we can scoop up in these volcanic sites takes you so far. There's also some labs that try to really accurately mimic the regolith that we would see on the moon, and they try to make these little glass inclusions as well, but that gets more complicated. Usually when we're talking about picking a simulant for an experiment, you're trying to figure out which characteristic are you trying to target. Are you trying to target the size distribution? Are you trying to target the shape of the particles? Are you trying to target the chemistry of the particles? Usually we can't exactly match all of those things when we're doing an experiment, but you might be able to match one or the other that is important for your experiment on Earth.
That's really interesting. And so you can just there's a way to shop for simulant.
Yeah. There's actually a website where they have a bunch of different simulants. You can look at their size distributions, their chemistry, cohesive properties, which is really important too. So yeah.
Order your own custom mix.
Yeah, there are some places that will make your custom mix, like if there's something very particular that you're trying to replicate.
That's really cool. And same goes for Mars too. Like you can get your hands on Mars simulant.
Yep. There's Mars simulants as well.
And how does that look different? Like if you look at Mars, I mean, I can't wait for us to get this first Mars sample return mission to come home. But if you looked in the microscope at what Mars regolith would look like, how would it be different from lunar regolith?
Well, Mars does have wind, so I imagine that those particles are going to be a bit more rounded than you would see like on the moon. Chemically, they're going to be different as well, right? Mars is very orange, the moon is not. So there's going to be some chemistry differences as well. We think that there used to be water on the surface of Mars. That's going to change the chemistry. That could also change the grain shapes. So I think there's definitely going to be differences.
So let's talk about the damage. We know from the Apollo missions that the lunar regolith got everywhere, gave the astronauts runny noses. Like what kind of damage can this stuff do in both the short and kind of long term to any exploration that we try to do on the moon?
Yeah, so there's a couple different ways that it can cause damage. The first is because those grains are so angular, when they get in like a joint, like you can imagine a wrist joint on a spacesuit, that's a joint that has to rotate repeatedly. Now, if you get a lot of grit in there, right, these very angular regolith grains, they're going to wear down that rotation mechanism. And so, just like if you got sand in like a seal right here on Earth, you can imagine how that would be gritty and it would be a problem. So there's that problem, just this mechanical abrasion. Then there's thermal effects also, which is not something that most people think of. But the moon is pretty warm in the day side, pretty cold on the night side, and we design our spacecraft for just the nominal lunar environment. So we think of like, okay, how much heat are we going to be radiating off of this surface based on its properties and based on the illumination conditions that we expect. If we get a layer of dust on the surface of our spacecraft, that's going to change those thermal properties. So actually, during the Apollo era, they had issues with overheating because there was dust that accumulated on portions of their instruments that, the thermal properties were no longer how they expected. And so that was a problem. You also have just the issue with optics being coated in dust. So we see this like on Mars, where we have solar panels that get this dust that coats them, and then they aren't able to produce electricity as efficiently as they were when they're uncoated. So that's just we're just simply blocking the sun from our solar panels with dust, which is also a problem. And then when you start talking about astronauts and you have spacesuits, right? Not only do the regolith grains get into joints and seals, but they also really embed in the fabric itself. If you go to the Smithsonian now and you look at the spacesuits, there's still lunar dust embedded in the spacesuits. They can't clean it off.
Right.
So, and it's kind of a catch-22 because some people are like, all right, well, if the dust is embedded in the spacesuit, then why is it a problem for astronauts breathing it, right? Either it comes off and they breathe it, or it doesn't come off, but it actually does both.
Right.
So sometimes, the large enough particles are going to be released in the crew environment, which is what happened on Apollo and kind of gave the astronauts the runny nose, kind of hay fever-like symptoms. But then there's other particles that just stay embedded in the spacesuit material, changing the thermal properties of the spacesuits.
Do we know what the long-term consequences are of this to the astronauts' health?
Not really. There are some studies going on right now trying to understand like how amino acids interact with regolith, how different cells interact with regolith, but I don't think we have a conclusive answer on that. It's primarily we would like to avoid having astronauts breathe in regolith. We know, like on Earth, that breathing in a lot of dust is generally not a good idea, especially really small dust particles that can get kind of embedded in your lungs. So we'd like to avoid it in a lot of the designs right now. When we talk about designing spacesuits, they're kind of designs where the spacesuit would always stay outside the habitat. And so the astronaut would kind of climb in through a port on the back of the spacesuit and then go off and do their EVA and then come back and then climb back into the vehicle. So the spacesuit would never actually come inside. And that's one idea of how to like separate, remove this risk to the astronauts.
Yeah, I mean, we know examples of dust here on Earth on the easier side. Yeah, you go into a dusty room and you sneeze and then it goes away. But with far more jagged particles, things like asbestos, it can be very damaging over the long term. And I guess regolith sort of fit somewhere in that spectrum from jagged to harmless.
Yeah, I mean, it's a size and shape effect, right? So those small particles can get deep into your lungs and get stuck there. And that's one of the things that we're concerned about.
Yeah. So you started to talk about mitigation strategies, and this is sort of the heart of your work. So what's to be done about all of this dust?
Yeah, there's a lot of different ideas about things that we could do to try to remove dust from surfaces. Some folks are also working on like special coatings that you would place on a surface that make it less sticky to the dust, so make it easier to remove dust from surfaces. Some of the interesting ideas are using electrostatics. So the moon has no atmosphere, and that means that the surface of the moon is actually interacting with the solar wind plasma. So this is like a soup of ions and electrons near the surface, and that can charge up the dust particles, the regolith, on the surface. So these are now charged particles. They're sitting on the surface. So there are some technologies that are interested in like exploiting that charge and seeing, okay, can we use this to help us remove particles from the surface? One idea that's been developed at Kennedy Space Center has been to embed kind of concentric electrodes, or almost like a grid of electrodes, into a surface, and then you apply an alternating current, kind of a traveling wave across those electrodes, and the dust grains, they're charged, so they respond to like the little electric field that is formed between these electrodes, and so they kind of hop across the surface until they clear that surface. So that's one idea that's had a lot of testing. There are other ideas that in my lab we've looked into, like having a kind of a magic wand that you would bias to some electric potential, and that electric potential would make an electric field between the surface and your wand. And then, the dust would be attracted to this wand. So you'd kind of have a wand that you held above your arm or whatever part of the spacesuit you wanted to clear. And the dust would be attracted to the wand and away from the spacesuit. That's another idea that we've been working on. Another thing that we've also looked at recently is using synthetic gecko skin. So gecko skin, like when you think of a gecko, they can walk on these vertical walls, right? Like it's pretty incredible, the sorts of things that geckos can do. And the way that they do that is on the surface of their feet, they have a bunch of little ridges. They're called setae. They're like little hairs. And what that does is when the gecko presses its foot on the surface, those hairs deform into all the like nooks and crannies on the surface, and it increases the cohesion between the foot and the surface. There's this synthetic gecko skin that we make on Earth, which is a silicone elastomer, and it has all these little hairs on it, and it's very cohesive. But the problem with it when we try to use it in robotic applications on Earth is that it gets dusty. And so one of my grad students was like, "Oh, this would be great if we used this dusty, weakness as a way to actually remove dust." So we took our synthetic gecko skin and we stuck it on a lint roller. And we actually have a gecko skin lint roller that you can roll across a surface and remove the dust, or roll
Does it work for
across
cat hair?
I haven't actually tried it with cat hair, which you would think I would, but I haven't.
A sample right there.
Yeah.
That's amazing. That van der Waals force will do the trick to remove the dust. I really like that. So which one, like when I think about the different strategies, like one is power hungry, I guess, if you're going to try and cover an entire surface, but it mitigates it at the source. The other one is, I guess, less power hungry, but you're having to manually move your wand around and catch every little nook and cranny. That sounds labor intensive and very time intensive. And then the other one with the gecko fingers feels,
we call it the gecko roller.
The gecko roller, yeah, I love it. Sounds very I guess mechanical on that sense. And again, like it won't catch the stuff that's in the nook and crannies. It has to touch it or get really close to it. Do you have a sense which one is more effective?
I mean, I think the ultimate solution is going to be a multi-pronged solution, right? So one of the weaknesses with like the gecko roller is that if you have to roll it across an optical surface, it might scratch things. It really might not be a great solution for that. In that case, maybe you want to have these embedded electrodes, right? Where it's a contact-free, we can remove the dust from that surface. From a thing like an astronaut spacesuit, you might want a gecko roller because it doesn't really require any power in the field, right? You could be on your EVA far from the habitat, and you need to clean an instrument that's far from the habitat, or you need to clean your spacesuit at like right now, not when you get back. So in those cases, it might be beneficial to have something like the gecko roller, right? There could be different times when it's appropriate to use different technologies.
And I guess there are areas of greatest concern, like these seals, the places where once the dust gets in, you're never getting it back out again, and you need to prevent it 100% of the time.
Yeah. So, removal mechanisms are not optimal and that sort of thing. You kind of want a prevention mechanism there. So I think there's going to be multiple solutions that we need to implement.
There was research that I saw fairly recently where they doused stuff in, was it liquid nitrogen? Did you see that work? They sprayed liquid nitrogen. I believe it was liquid nitrogen, and it did a great job. Like it was like water off a duck's back, that the particles collected the dust particles and then carried it away from it quite effectively. and in a non-damaging way. So there's no damage at all to the underlying fabric, while other methods are. So it sounds like it's going to be this kind of, there's going to be many different ways to mitigate this dust at different scales, depending on the severity of it and so on. So,
yeah. And if you have a human that is actuating something versus an autonomous robot that needs to actuate something, and then there's the issue of, if it's an autonomous robot, how do we tell that something needs to be cleaned?
Do you think that we understand the scale of the problem? Like I feel a bit like we have this overly romantic idea of what it's going to be like to live on the moon. That it's just going to be, we're going to be bouncing around on the moon. It's going to be great. But is it that, or is it much more like what it's like to be on the International Space Station, where you spend hours every day working out to try to mitigate the bone loss? Like the level of maintenance required to just exist on the moon is going to be beyond what people are expecting.
Yeah. I mean, it's definitely going to be a remote outpost,
Yeah.
It's going to be more like camping in a, remote place where no one can save you, right? Than our normal day-to-day existence.
And I think like I want to go for a walk outside, and then, the mission controller will be like, fine, but tomorrow you're going to spend the whole day cleaning off the dust off your EVA suit,
right?
And everything you touched, for your 30-minute walk outside to go see the sunrise or whatever, right?
Yeah, I mean, it's just a very different. It's not like our normal day-to-day life. I think of, people that are living at the South Pole for a year, or living like in these very remote environments with only a small group of people, limited freedom, right, to just go take a walk. I think it's going to be a whole lot more like that than our normal day-to-day life.
So whenever we talk about rovers dying on Mars, just my comments fill up with people saying, and it's very much, it's hard to read, because people are just like dunking on NASA and saying, like, why didn't they just? And then they provide, like, why didn't they just install wiper blades? Why didn't they just tilt the panels? What are people not getting about this dust, especially in Mars, that makes it so tricky to mitigate for a mission like Spirit, Opportunity, Jurong rover, InSight? Like, the list goes on.
Pretty much all of them, right?
All of them, yeah. Anything solar paneled is on borrowed time when it goes to Mars.
Yeah. I mean, I think that the characteristic of dust that is most non-intuitive is that it's very cohesive. So it's very sticky. It's more like flour than it is like sand. When you bake with flour, right? Like, you pour that flour from your bag into your bowl, and it's really clumpy. And that's because it's cohesive. Like, if you pour sand into a bowl, or even sugar into a bowl, right? It's just very uniform and kind of smooth. And so that's an easy way to think about cohesion here on Earth. What this means is that the dust is very sticky to everything. So it really wants to stick to that solar panel. And there are these very small particles and angular particles, as we talked about before. So if you try to brush something across the surface, you could just really scrape up that surface. You could have a problem where that windshield wiper gets stuck halfway, and then what are you going to do now? Your windshield wiper is creating it's like a sundial. It's creating a shadow on your solar panel for half the day. Tilting the solar panel, the stuff's just not going to roll off, right? Like, we use this in baking all the time. You take your flour, you stick it in the pan, you roll it around, you tilt the pan. There's still flour in the pan, right? I mean, you have to wash it off. So it's very cohesive. And because gravity is weaker on these bodies, cohesion, which most of the time we can neglect on Earth, becomes a more important force that you have to really worry about. And stuff behaves in non-intuitive ways because of that, right? It's just different from our terrestrial understanding of how soils and grains move around. And really just the study of grains, all, grains of different sizes, from gravel and corn particles down to flour. Like, it's such a common material here on Earth, but we really don't understand the fundamentals of it. Like,
That's amazing.
Granular materials is an open area of physics right now. There's a lot of work to be done, and it's so common you'd think we'd understand it, but we really don't, because it's kind of somewhere in between a solid and a liquid. It's like a bunch of solids that when they move together, they behave like a liquid, like in an avalanche. That's really kind of a liquid flow, but made out of small particles.
I mean, I think about like the rear window of your car after you've been driving in muddy, dusty terrain. And imagine you just took like a gentle windshield wiper and sort of scraped it across. You're not going to clean it off. Like, you need water, soap,
Right.
An attention to detail. So Imagine you were an astronaut and you were tasked to go out there and clean the solar panels, and this was part of your maintenance job. What would it take for you to get those solar panels back up to 100% efficiency?
Yeah, I mean, it would take technology that I don't think we have right now.
It would take technology that you don't think we have. Like, like people are imagining, like, I walk outside with a bucket filled with water and a cloth, and I try scrubbing it. Well, your water sublimates away or freezes solid in the Martian environment. Your cloth freezes solid because it's covered, and then it sublimates while you're getting a giant dose of radiation.
It's just totally foreign to, like, I mean, because this is something we do all the time. You wash your car, no big deal, right? But it's like just totally a foreign environment.
And so do you think with Mars, like, some kind of electromagnetism is going to be the solution again to sort of push this stuff away before it collects?
I think some of the same technologies that are used on the moon, or that will be used on the moon, could also be used on Mars. On Mars, you might have the benefit of like harnessing some atmospheric effects, right? So dust devils are interesting because we see these dust devils go across, and sometimes they actually clear off solar panels, right? They can scour surfaces. And there is a small atmosphere on Mars. So, maybe we could collect some of that atmosphere and make a compressed gas that we can blow surfaces off with. That would be hard on the moon because we have no atmosphere. So it would be a very consumable resource. And we try, everything that we have in these places is, either stuff we bring or stuff we harvest. So on Mars, potentially we could harvest a gas that we would then compress, which would take a lot of power. But I guess that's what I would think would be the additional options on Mars could be things that use a gas. Whereas on the moon, I don't think that that's as feasible because you'd have to bring all that raw material with you.
Right. Yeah. Yeah. I mean, if you are going to take your liquid nitrogen spray, your electromagnetic wand, your gecko roller, you're going to have to bring all that stuff from Earth.
Yeah.
And you have to be on it all the time because otherwise, the seal on the glove that you depend on to not die has to remain perfect.
Yeah.
For your mission. Oh, it just sounds anxiety inducing. I like Earth. Yeah. Earth is the best.
Yeah. The Apollo astronauts, they had quotes that they're like, "I'm never dusting again when I get home." Because they'd spend tons of time they had brushes. That was their mitigation technology. And so they'd spend a lot of time brushing off each other before they went back into the vehicle. And, there are transcripts of them saying, "I'm never dusting again. Dust is the biggest problem, for long-term human presence on the moon."
Yeah.
So
it's funny. So in cosmology and in astronomy, astronomers complain about dust all the time, that dust has been the downfall of so many amazing results. Like, we've discovered the shape of the Milky Way. Oh no, wait, it's just dust. We've figured out how old the universe. Oh no, wait, it's just dust. And so this sort of constant enemy to cosmologists turns out is also the enemy to space exploration. Like, dust is like the number one problem that we have to deal with. And so when you think about dust in your home, you're in good company.
Yeah, that's right.
It's awful. Well, Dr. Hartzell, thank you so much for taking the time to chat with me today. And if anyone comes up with good ideas to mitigate dust, should I send them your way or just hang on to them?
Well, NASA's definitely interested in it. So,
yeah. Wonderful.
All right. Good ideas are the way to go.
Yeah, definitely. All right. Well, thank you so much.
Thank you.
You can get even more space news on my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Vlad Shipolin, Jay Dennis, David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.